Hi, we're going to look at the number 6 problem from the 2011 AP Statistics exam. These are typically called like your extended task. These are longer than the first 5 problems. Let's take a look at this one. Every year, each student in nationally representative sample is given tests in various subjects. Recently, a random sample of 9,600 12th grade students from the U.S. were administered a multiple choice U.S. history exam. And here was one of the questions. Okay, of the 9,600 students who took the exam, 28% answered the question correctly. I think it's good to label that right away. Since that's a percentage based on a sample, we call that p hat. So p hat is 0.28. And let's make a note, our sample size is 9,600. Part A, let P be the proportion of all United States 12th graders who would answer the question correctly. Construct and interpret a 99% confidence interval for the true proportion P. Okay, so that's called a one proportion Z interval. I wrote test, sorry, but I should write interval there. In order to use that, there's a couple of assumptions you're supposed to check. Number one, you're supposed to have performed an SRS, which was stated in the problem, so we can check that off. Number two, you'd like to check for independence. The population of all 12th grade high school students in the U.S. should be greater than or equal to 10 times our sample size, which in this case is 9,600. So we get 96,000. Well, there's certainly more than 96,000 12th grade students in the U.S. And because this is true, because this works out, we can say that the standard deviation of p hat is equal to the square root of p hat times 1 minus p hat over n. While we're at it, why don't we just calculate that? So it's going to be the square root of 0.28 times 1 minus 0.28, which would be 0.72 over 9,600. So if we do this correctly, we get, hold on a second here, using my TI-84, we get around this 0.0046 when we round that. Okay, the third assumption is to check for normality. So if you want to make sure that we can use a normal distribution here, you need to check that n times p hat and n times 1 minus p hat are both greater than or equal to 10. So in the first case, we would have 9,600 times 0.28. So if we do that, we end up getting 2688, which is certainly greater than or equal to 10, so we can check that off. Then I would do 9,600 times 1 minus 0.28, which is 0.72. Let's see what we get here. We end up getting 6,912. It's always fun to notice that these two numbers will add to your original sample size. But that makes sense because these two percentages here add to 100. All right, so now we know that p hat is approximately normal. And we're ready to compute our one proportion Z interval. So the format of the interval is this: p hat plus or minus Z star square root p hat times 1 minus p hat over n. And our p hat is 0.28. Our Z star is going to remain blank for a moment. And we calculated this value already when we did the second assumption, just in case you forgot. It's right here, 0.0046. So I'm going to put that in here, 0.0046. Now, to get the correct Z-score that goes here, you should draw a normal distribution and shade some area in the middle that equals your confidence level, which in this case is 0.99. So we're shade in this area, and then we want to ask ourselves what Z-score should go here to capture the area that's in this tail. If there's any doubt about how to get that area in the tail, just think about it this way. The normal distribution is symmetric. And we know the total area under the normal distribution is 1. So if we do 1 minus 0.99, subtract out the middle, and divide by 2, we end up getting 0.005, which is exactly the area in this tail. Once you have that, it's good to use inverse norm Oh, that's a little bit sloppy. Hold on, I forgot that. So that's an INV and then norm, NORM, 0.005, comma 0, comma 1. To find that function, you do second vars, second distributions, and it's the third item, inverse norm. It will ask you for an area, put 0.05, 0.005 that is, sorry. Leave the mean at 0 and the standard deviation at 1 because we're looking for a z-score. And then we get z equals negative 2.576 when rounded. In the confidence interval, I would just put the positive version of that, 2.576. Okay, so if we compute these two values, here's what we get. We do 0.28 minus 2.576 times 0.0046. And if we do the minus one, we end up getting the following. We end up getting 0.268. And then for an upper bound, we end up getting 0.291. So what's the interpretation of this? We are 99% confident that the true proportion of all 12th grade students who would get this question correct is somewhere between 0.268 and 0.291. Okay, so that's part A. Let's move on. They tell us in this next question, there's a little statement here we just got to read carefully. It's snuck in here. I'm going to highlight that here. Actually, and also the thing above it that I'm going to circle in green. So they're telling us two things here. They're saying, assume that students who actually know the correct answer have a 100% chance of answering the question correctly. That might seem silly, but I guess what the author's trying to say here is that you could have a kid who knows the answer to the question, but then maybe circles the wrong choice, makes a simple error like that. We're saying that that's not going to happen. And then we're also going to assume that students who do not know the question are going to completely guess at random from one of these four choices. So if the kid doesn't know the answer to the question, they're just going to guess. They're not going to be able to eliminate any choices or anything like that. And then it's subtle, and they say right here, let's highlight that in a different color. Let K represent the proportion of all 12th grade students who actually know the question. And then they give us this pretty tree diagram. So the tree diagram of possible outcomes for randomly selected 12th graders is provided below. So here's what we're looking at, right? So here's that probability K, the proportion of kids who actually know the answer. And sure enough, if they know the answer, then the probability they guess it correctly is 1. Or not guess it correctly, but answer correctly is 1. If they know the question, they're not going to get wrong, which is why that probability is 0. So this probability out here was just K times 0, which is why it's 0. And this probability over here is K times 1. So that's how that is. All right, so down on the bottom now, the probability that they get the question wrong is 1 minus K. That's if we're picking a random student. We know K% of them know the question, so 1 minus K do not. The conditional probability they guessed correctly, well, it's subtle, but it's hiding in the question. They said that the person would just randomly guess from the four choices. So it means they have a 1 in 4 chance of guessing correctly. As opposed to the person guessing incorrectly, there's a 3 out of 4 chance. All right, so now to get these probabilities, for example, this probability, you just take these two things and multiply them. So we can write 1/4 minus 1/4 of K. And then here on the bottom, these two probabilities, we can just multiply those and we'll get 3/4 minus 3/4 of K. So there you are. That's the tree diagram. Let's see what they tell us now. Based on the tree diagram below, tree diagram, express the probability in terms of K that a randomly selected 12th grade student would correctly answer the history question. So there's two places where the person answers the question correctly. One of them is up here, just K, because the person knew the answer and picked the right choice. And the other one is down here where the person didn't know the answer, but they managed to guess correctly. So we just need to add these two cases together. So the answer, part C, is K plus and 1/4 K minus 1/4 of K, which when added would give you 1/4 plus 3/4 of K. So there you have it. That's the answer to part C. Okay, so here comes, usually with these explorative tasks or these investigative tasks, these longer problems, the last problem, the last part of it is usually tricky in some way. So this is usually where things get difficult or you got to be creative. Let's see what this one says. Using your interval from part A. So just to remind ourselves, that's this one right here. So 0.268 to 0.291. So I'm going to make a note of that. 0.268 to 0.291. And your answer to part C, which is right here, calculate and interpret a 99% confidence interval for K, the proportion of all students who would actually know the answer to the history question. You may assume the conditions for inference in the confidence interval have been checked and verified. Okay, so how can we use these two things together in a clever way? All right, so what we know here is that the variable K represents the proportion who actually know it. That's from the tree diagram, right? That's here. So that's a part of the total number of people who would get it correct. Here's the other part down here. So we added those together and we know that those people would get the questions correct. So what I'm going to do is take this 1/4 plus 3/4 K and set it equal to the boundaries of the confidence interval for the people who answered it correctly. Because the people who answered it correctly, that group is actually made up of two groups, people who actually knew the question and circled the right choice, and then also people who didn't know the question but lucked out and picked the right choice randomly. So we're going to solve for K in each of these equations to get a new confidence interval, which represent the proportion of people who actually knew it. So I'm going to 0.268 minus 0.25, here we are, divided by 0.75, and we end up getting here 0.024. That's when you solve that equation. You solve this equation. Just give me a second here. I'm doing 0.291 minus 0.25, and then divided by 0.75, we end up getting 0.05. It looks like 54, about that. So what we can say here is that we're 99% confident that the proportion of people, the proportion of 12th graders in the US who actually knew the answer to this question is somewhere between 0.024 and 0.054. Okay, thanks for watching.